Hello everyone, my name is Sim Harbert and I'm a senior research engineer at the Georgia Tech Research Institute. My presentation is on a virtual reality robotic cutting design framework. It was created through the funding by the Agricultural Technology Research Program of the state of Georgia. Thank you for your interest in the presentation.
As an introduction, I wanted to point out the problem we were trying to solve. It is difficult to optimize cuts and then implement them with automated systems. As research continues to improve dynamic cutting robots based on various sizes and types of birds, an automated technique for optimizing the cutting trajectories would be useful. Most of the time currently, tedious tests are performed on real birds to assess size impact on the efficacy of various cut trajectories. This involves large number of birds and many hours of work. Our solution is to improve current state of art related to producing better cutting trajectories and paths by using virtual reality. We wanted to create high-fidelity bird models with skin and skeletal structures that can be imported into the VR environment. This will allow us to demonstrate cut trajectories in VR. Then those cutting trajectories could be transferred for testing on VR-based robot arm as well as to a physical robot arm for further testing on real birds. This system would be used to refine the equipment designs for research and eventually, we hope, industry. I wanted to outline the process for creating the high-fidelity bird models that we need for the VR environment. We first start by scanning real birds using CT imaging. We scan many birds in order to have the wide selection of shapes and sizes. The image in the upper left shows the scanning operation, including bins where the birds were placed and then the CT scanner. Once the birds were scanned, we use specialized software to convert the raw CT scan and create the skeletal model and the corresponding surface skin model that use density of those generated by the CT scan. Those models are then exported to a format that can be imported and used in the VR environment, as can be seen by the lower left image. After creating the bird models for the VR environment, as was previously mentioned, we then came up with a way of taking the VR cutting trajectories from the VR environment into the physical robot environment. This was done by creating what we called a system communication pipeline to allow for a seamless transition between virtual space and physical space. This required custom code to implement. Trajectories could be created and saved in VR space and then tested on a robot arm in the VR space as well. And from there, the trajectories could be tested on a robot arm in the physical space. The system communication pipeline was created to allow for communication between the virtual space and the physical space. An effort was made to create a means to seamlessly transition between the virtual and physical spaces. To achieve this, a bridge was developed that can be accessed by both spaces, which is the trajectory calculation module. This slide shows how the virtual space and the trajectory calculation module interact. The virtual space displays the mesh of the chicken. This model is then defined by the user as a certain type of chicken, something like either large or small. And then reference points are identified on the chicken, such as the shoulders or tail, and that information is passed to the trajectory calculation module. In the trajectory calculation module, cut points are generated that are smoothed using a spline function and turned into a knife trajectory. The cut points, as well as the knife's trajectory, are passed back to the virtual space module, where they are visualized and edited in the virtual environment. Here we are looking at the interaction of the physical space with the trajectory calculation module. It is similar to the interaction with the virtual space. First, a physical chicken is arranged near the robot, and we identify the chicken as a certain type, say large or small, as previously. We then identify reference points on the chicken, such as the shoulders or tail, and using the robot end effector to do that. That information is passed to the trajectory calculation module. In the trajectory calculation module, cut points are generated and they are smoothed using a spline function and turned into a knife trajectory. The cut points as well as the knife's trajectory are passed back to the physical space where the cut can be performed by the robot. One of the interesting things we discovered when creating the system communication pipeline was a problem in dealing with coordinate systems. It turns out to be more complicated than you would think to go between the left-handed coordinate frame of the Unity VR system we were using with the physical robot that was using a right-hand coordinate system frame. Most will just convert by negating the x value in one frame to the other, but this makes more complicated transforms not valid. For our system, we created a way of tracking the left-handed coordinate frame and the right-handed coordinate frame environment of the physical space. By doing this, we were able to do transforms such as rotations, reflections, translations, and then pass things properly back to the left-handed coordinate frame of the VR space. Here we have a video of the VR app we created that allows for creating and editing cutting trajectories by specifying locations and orientations of the knife blade on a VR model of the bird. The bird model is selected from those currently available, and then the number of points for the trajectory is selected. After that, the knife blade models are positioned with the tips along the cutting trajectory that we want. They can be rearranged until they are in the right positions. Those points specified will be used for creating a cutting path by smoothing along the spline function. This will be done by the trajectory calculation module. Here in the video, you can see that the static knife models specifying the cut points as well as the knife that is moving along that calculated path. That knife blade route is being calculated on board the VR system. Once all of the points are in the right position, then the trajectory can be saved to the calculation module for further testing in either the virtual space or the physical space. In this video, we demonstrate testing the cutting trajectory using the virtual robot arm. This arm retrieves the cutting trajectory from the trajectory calculation module in the same way that the physical arm would do. The arm then follows that path and the knife with the knife blade end effector. No collision detection is being performed between the robot arm and the bird arm, so the arm doesn't always make the appropriate path. This is currently being optimized to avoid these collisions, and further work needs to be done here. Here we see the initial test of pulling the entire pipeline together by having the physical robot follow the cutting trajectory after asking for it from the trajectory calculation node. The robot operation still needs a lot of tweaking and is operating at a slow speed. We will be looking at making changes to the path calculation to improve much of that. But this illustrates the success of creating a cutting trajectory in the VR environment, passing that to the trajectory calculation node, and then implementing it on the physical robot. As you can tell, it takes a while to complete. This video is from previous research showing the robot doing a cut on a real bird with a trajectory created in the VR environment. We also explored creating a deformable bird model for the VR environment. This would allow for more positions of wings and legs to represent different orientations of the birds. Here you can see the bones have been separated and joints have been added. The segments of the legs and wings can be moved, but they stay attached at the joint. This also works for the surface skin model that deforms continuously. Our research created the initial software-hardware pipeline between VR and physical world. This included fixing errors going between left and right-hand coordinate systems, as well as handling many software interfacing issues. The entire software communication pipeline setup is modular, allowing the components, the VR environment, the trajectory calculator, and the robot controller to run on separate machines. The initial version was tested, but further tests with physical robot on the real birds was not achieved. Further work, there needs to be a refinement of the software that includes better usability and better control of the robot. And new models for more types of birds would also help, since they are rigid and not necessarily in the same position we want to test with. Thank you for listening, and if you have further questions or need more information, my email address is right here.